is Vicent Peris, who comes to us by way of the University of Valencia, the Astronomical Observatory there, where he's the astrophotographer. Vicent has also been a developer for the PixInsight software image processing platform. He's been working with them for about 10 years, developing different algorithms for image processing to help bring the most out of your data for astrophotography. In particular, he developed a really powerful high dynamic range tool that allows you to pull details out of images with a lot of dynamic range in them. And more recently, Vicent has also been working in sort of crime scene investigation type situations where he has helped the police in Spain to solve certain crimes. And he'll speak a lot more about that in his talk. So I don't want to take any more time away from Vicent. Here we go.
Okay. Okay. Hi everybody. First thing I want to give. Oh, it's on. Okay. First, I would want to thank Joe for organizing this event. It's a very unique opportunity for me to come here to speak to you. Well, I have been working as astrophotographer in the Astronomical Observatory of the University of Valencia during the 7 last years. And I'm going to speak here about some of the projects I have been involved. One of the projects is the development of the PixInsight platform. PixInsight is an advanced image processing platform that has been developed from within the astrophotographic community. So we could say that it has been developed by astrophotographers, for astrophotographers, and it has very specific tools for the needs of every astrophotographer. PixInsight has been imported natively, very important, to FreeBSD, Linux, Mac OS X, and Windows operating systems, and is available as a 64-bit application. But PixInsight is also a software development framework. So every user can program new tools, okay? And the user can program these tools in 2 different languages. In C++ through the PixInsight class library, or in JavaScript through the PixInsight JavaScript runtime. But PixInsight is more than a software platform, because PixInsight represents a working philosophy, and this philosophy materializes in the Documentary School of Astrophotography. We created this school because we do think that today astrophotography is at a critical point. Long time ago, when we had only chemical film, it was relatively easy to discern where work was honest or not. But now, with all the processing tools we have at our reach, it is not as easy. We think that astrophotography is documentary photography of the sky, but unlike other photographic disciplines, astrophotography has very unique properties. One of these properties is that the photographer is not able to see what's photographing. So in this way, the image processing is the link, the direct link between the data set and the spectator. This means that the astrophotographer must respect, above all, the acquired data and the nature of the objects, because in any way the spectator is going to be able to check if this work has been honest or not, because the spectator is not going to see those objects visually. And in this way, the documentary school only accepts as valid image processing practices those that have documentary criteria. And we understand these documentary criteria as those that pretend to communicate some properties of the photographed objects. Well, some of the first projects we had in the documentary school was an astrophotography project at Calar Alto Observatory. Calar Alto ordered to make a photographic work with their telescopes. And this is a very unique project because it is the first astrophotographic project to have direct access to the observational time of professional telescopes. We have around 50 nights per year in this telescope, 1.2 meter telescope. And I'm going to show you some of the techniques we apply to build our images in this project. Some of these techniques are commonly used in astronomy, but we use these techniques with the goal of visually communicating a natural fact. In astrophotography, narrowband imaging is very important because it lets you to show some physical properties of the objects. In this example of the Stefan's quintet, we used two different H-alpha filters. One at the regular H-alpha waveband for the foreground galaxy. And when we subtract the broadband air image from this image, we get isolated all the H-alpha structures from this galaxy. Then we used a second H-alpha filter, but at a longer wavelength to compensate the redshift of the main galaxy group. And we did the same subtraction to isolate the H-alpha emission from this group. And then we get the two H-alpha emissions and mixed them into the color image. Okay, but we did a mixing with a different color coding for each waveband. So the regular H-alpha was introduced as pink, and the redshift H-alpha was introduced as pure red. In this other example, we used again narrowband imaging techniques. It's the core of the Andromeda galaxy, and here we used 4 different filters. 2 of the filters were centered on emission lines, here on H-alpha and here on H-beta and oxygen 3. Then we are going to do the same technique for continuous subtraction, but we are using the technique described by Fernando Ballesteros in New Insights into Black Bodies. In this article, he describes how to calculate the black body radiation at a given wavelength from 2 other wavelengths. So from these 2 filters, we calculated the black body radiation in this band and in this band when we have strong emissions. And in these 2 bands, we don't have any strong emission line. So here we can see the oxygen 3 image, but after calculating the black body radiation of this image and subtracting that from this image, we get this result where we almost remove all the galaxy, and we only have here some small dots that are almost all planetary nebulas inside the galaxy. See that some of them are not visible in the original image. So this lets us to enhance these objects in the color image composite. So this is the original color image, and after enhancing these objects, we make these tiny objects visible in the color image. And almost of them are planetary nebulas, but we have also here, and I think it was here, and here, 4 nova candidates. These stars also emit strongly in each alpha, so they are pink instead of blue. Okay. Another problem we used to face in astrophotography is that the objects contain at the same time very bright and very faint areas. And being documentary photography, we think that it's of extreme importance to show all the content, all the information content in all the areas of the object. This is why we apply dynamic range compression techniques. In PixInsight, we have our own solution for dynamic range compression, and we use an algorithm designed based in multi-scale processing methods. These multi-scale techniques divide the image in several components, and each component contains only structures of a given size. So in the 2-pixel scale, we can see, we can see the fainter stars and the smaller structures inside the main galaxy. If we go to the 8-pixel scale, we will see the brighter stars, and the spiral structure is starting to appear. But if we go up to the 32-pixel scale, we will see only the spiral structure of the galaxy. Our tool for dynamic range compression works on these image components separately and adjusts the contrast between them, and lets you to compress the dynamic range and show in a single image all the areas of the object. Compared to classical multi-scale techniques, we are going to recover the data inside the brighter areas. Here you can see the 4-pixel scale of the Abstruse-Weil algorithm, and you can see clearly that we have lost all of the contrast in the inner areas of the image, of the nebula. But with our algorithm, we recover all the contrast in the inner part. Another advantage of this algorithm is that the formulation is quite simple, so it's very fast to calculate, and it's also very easy to use, because most of the time we'll work with the default parameters, but in case you need to modify something, most of the time you will most of the time you will need only to modify the number of layers parameter. So it's a very stable solution and simple to use for people that does not understand too much about image processing. I'm going to show you some examples. This is another view of the Orion Nebula. It has exposures from 5 seconds to half an hour. Yeah. Thank you. This is before the processing, and this is the result just after one mouse click. Okay. This is a wider view of the Andromeda galaxy, and this is the result. And this is comet Pan-STARRS. And this method also works with non-astronomical images. Here we can see an aerial photo of the Pyrenees mountain range. It was taken with a very sample digital camera, and the original source is a JPEG image. This is before and after. See that the algorithm also removes the blue gradient coming from the atmosphere. And here you can see an example on a computer simulation of fluid dynamics. At the left, there is the original image, and to the right, the processed one. This is a single frame of a full movie that was processed with this algorithm. Well, apart from this project, I have been also collaborating in a big research project. This is a big collaboration mainly done by Spanish astronomers. And Alhambra survey is a cosmological survey that covered only 4 square degrees of the sky, but it's very deep, and it was done with the 3.5 meter telescope at Calar Alto. It uses the techniques, the photometric redshift technique, and in this technique we use a lot of filters, a lot of narrowband filters. In this case, 20, covering the full visual spectrum down to the near infrared, and in this case we used also 3 wideband in the infrared. But the important thing is that with these 20 filters we are able to reconstruct a very low resolution spectra of every object in the image. So this is a very good cost-effective solution, because in one data set you are getting the spectrum of thousands of objects. Here you can see an example of a distant galaxy, and it has a high redshift because you can see nothing from 500 nanometers. And this is the reconstructed spectrum, or well, it's photometry, but it says you some spectral information. Well, the challenge of this project was to give to communicate the content of those 23 filters in a single color image that is based only on 3 color primaries. Okay. This project also helped to develop how we understand color in astrophotography today, because in daylight photography we take as color reference the sunlight, and this is also done many times in astrophotography, but this didn't work with this project. First, because there is a lot of information outside the visible range. Here we can see a color composite only from the visual spectrum. And if we include the infrared wavelengths, we see that there appear a lot of objects that don't emit anything in the visible. And well, the other reason why why sunlight doesn't work in astrophotography is because the sun is not a significant object here in the images. To establish a good white reference, we should look for an object that is significant in the data set. And we thought that this significant object could be a face-on spiral galaxy. And this is because these galaxies contain a good proportion of all the stellar populations. If you put this as white reference for the photos, you are spending the tone representation of all the stellar populations. So what we did was to do photometry of 7 spiral galaxies inside the survey, and we established the addition of all the light coming from these galaxies as white. Okay, so this will be our white reference for the whole survey. This is the photon calibrated image, but when we apply this color calibration, we get this result. And here we can see clearly in the upper left side of the image how we can see the blue spiral arms of the spiral galaxy, or we can see clearly here all the old populations of the elliptical galaxies, or we can see also some tiny objects which are very blue that are possibly starburst galaxies. And after doing this calibration, we wrote a script that automates all the processing of the survey. So this script generated 3 synthetic filters, RGB filters, and you can modify the shape of the band of each filter. And here you can see some of the results. The survey is plenty of mergers, several types of galaxies, some very, very red objects also. We can see also some very distant galaxy clusters that are completely red. And here I will want to zoom in this area. We have here a nice merger, but take a look at this spiral galaxy, because it's not a common spiral galaxy. Of course, it has some blue arms, but the core of the galaxy is also blue. And when I asked to retrieve the photometric data from this galaxy, I saw that the galaxy has some emission lines in the spectrum at a redshift of 0.16. So with this processing engine, we are communicating different types of galaxies, different types of stellar populations, and redshifts concepts, and but also the emission lines or some characteristic objects that are very uncommon. And well, my future plans for this engine is to put it to work with this project, this new project in Spain. Is the Hablhambre physics of the accelerating universe survey. It will employ a higher resolution camera and a filter system consisting of 50 different filters. So my idea is to put a computer that will process automatically all the new data sets and create color images for science outreach of the project. Last thing I want to talk to you about astronomy is about photometry. I have developed an aperture photometry script in PixInsight with another user, Andres del Pozo. And in this script, we can do automatically the aperture photometry of a file list. The script also does automatically the plate solving of all the images. And this script works by selecting catalog stars. So you can choose the catalog and the server. It will connect through internet to retrieve the data, and you can set also a maximum magnitude. And regarding the apertures, you can select a range of apertures. So all the measurements will go to the same text file. Here you can see an example of a transit of an exoplanet. And this script is being used now in a research program led by Roberto Abram and Peter Van Dokkum. This project uses an array of wide-angle lens to image near galaxies to search for ultra-low surface structures around them. The script is doing now the photometry of all the stars in the Sloan system. And at the left, you can see the graph showing the ratio between the image fluxes and the catalog fluxes. So from these measurements, we can derive a residual gradient in the image. And then we can apply, well, the tool creates this image that is the residual gradient. It is then applied to the original image as a second flag. And here you can see the photometry after this correction. And well, I'm going now to speak about forensics, because from my developments in the PixInsight platform, I appeared in the national TV news, and some police decided to contact me to help them in some specific cases. I have been collaborating during the last 3 years, and I'm going to talk to you about a single case, because it's very inspirational in my opinion, because I employed techniques commonly used in astronomy for solving this case. I'm going to show you some videos, because all the material I had were very low resolution videos. Well, this case was a double murder of two kids of 6 and 2 years old. And well, at that time we didn't know if it was a murder, because the children were disappeared, supposedly disappeared. But at the end we find that the father killed them in a bonfire, and he put an iron table on top of the bonfire to raise the temperature to 1,000 degrees. So to completely eliminate any trace of DNA. The police gave me some videos. This is of one street. The first day of every investigation is very critical, because you are looking for those videos that usually got erased from the recording machines. Here you will see the suspicious car here passing through the video. Okay, and the police asked me if I could read that plate in the car. Obviously, it's not possible to read the plate, but I will show you how I get to identify the plate. The first thing I thought it was necessary is to improve the image quality of the single frames. So, like we do in astronomy, I combined a set of frames, I had to deform every frame to fit the plate position. So at the left, you can see a single frame, and at the right, you can see 11 combined frames. Maybe we are losing some sharpness of the right, but the information content of this image is more reliable than a single frame. And you can check that the car edges are much better reconstructed in the combined image, because the JPEG compression was distorting the edges. So this was, in my opinion, very important to get the most of this tiny plate. Then I did the same with a lot of cars passing through the video camera. And I collected all the plates. And I had two plates from the same car passing through the video camera in the crime day. But I had also 4 plates from the polished reconstructions. These polished reconstructions were very important because the police used the suspicious car. So my goal was to demonstrate that the plate in the crime day was the same that in the reconstructions. And this is my small collection of plates from the cars passing through the view camera. And what I did was, well, at that time, the scientists in my department were working with the Alhambra survey. And when you have a galaxy in Alhambra survey, you have very few data from the 23 filters. But you can compare this data with galactic templates, and you adjust the model with a chi-square test. So what I did here was exactly the same. Here I'm going to show you this example. Here we have a lot of plates. 2 of them are identical, but now we blur all the plates. And this blurring is not uniform, so each plate has a slightly different blurring. And now we order all the plates, and we are going to find the identical plate. We run the chi-square test, and we got a very low value there. And the second lower is up there in the green square. When we uncover the plates, we have we have found the identical plate, and the second one has different letters but the same numbers. So what we did was to compare each plate with all the others. So at the end we had about 400 comparisons. And when we plot all the results of the chi-square test, all the plates from the suspicious and their reconstructions go to the left, to the minimum values of the graph. There are also some very low values, but we saw then that we had several cars passing several times through the video. So this test allowed us to recognize also these cars. And it's also a double check for this technique. Okay. The second video I'm going to show you was very important in the case because it allowed us to reduce the search radius of the kids from the whole Europe to 5,000 square meters. Here you can see one street, and here at the end of the street we have the crime scene. Here we cannot see almost anything, and we see some cars going, and then it will appear the suspicious car. One moment, this one. So my work here was my goal was to track the car movement, because when it reaches the road at this point, you almost cannot see anything. But the car could enter the crime scene or could just go straight on the road. Okay, so this was very important to check where to look for the kids. Okay. The beginning of the solution of this crime is in the key difference between these two images. There is a difference that will be fundamental in this investigation, and is this structure here. It is a white electrical post that is very far from the video camera, but when I checked on the Google Street View, I saw that the electrical post is made of concrete instead of wood. So in the afternoon, it reflects a lot of sunlight to the camera. And I was so lucky to find that this electrical post was struck in the line of sight between the camera and the entrance door to the crime scene. So with this electrical post, we can pinpoint where is the pixel with the entrance door to the crime scene, even if we cannot see it. Okay, so we have located the entrance door, but in any way we are going to check what's happening there. Therefore, my idea was to play to the 7 differences game. Here we have 2 world maps, and there are 7 differences between the 2 maps. If you take some time, we will find the differences between them. But it will take some time. This is the problem, because in a video we have thousands of images, and then we cannot do this game in those all image set, because we need an objective vision of the video. What I did was to take this in the first image and then subtract the second image, and then we have as a result only the differences between them. So we are looking exactly at the differences, not at the image itself. Then I combined 500 images and did a reference image. This image was combined with a sigma reaction algorithm, so all the moving objects I removed for a reference image. And then we subtract this image from all the video frames, and we get this result. Here you are looking only at the moving objects, and here this small red dot is the position of the entrance door. So if we are lucky, we will see the suspicious car going into the red square. This first car is important also in this case, because you can see the car moving farther than the entrance door. So we can state that we can look at the objects going into the crime scene. You will see other cars and other coming to the front, to the foreground. A bit of patience. This is the car. The car now is in front of the entrance door. We will see that the car is now turning right. It reflects more sunlight to the video camera. And then it goes inside the square. Therefore, we can say that the car entered the crime scene, and the police had 3 hours in which they didn't know anything about the suspicious, because he disconnected his mobile phone. So I processed about 5 hours of video and found that in those 3 hours nothing happens in the entrance door. So the car was always in the crime scene in this time. And this investigation weren't very complicated, because there was a huge error by an anthropologist that identified the bones of the kids as being of animals, of small animals. So the police was looking for the kids for about one year outside the crime scene, and when I gave them these results, they concentrated on this scene, and then a second anthropologist did a second analysis to the bones, and then we found that the bones were from the kids. Even if there were any trace of DNA, we were able to identify some teeth that appear are very concrete ages. So we could say that those child have the same age that the disappeared child. So, okay, this is everything. Thank you very much. And if you want more information about my work, you can visit the observatory website, my own website, PixInsight, DSA, or Calar Alto Observatory. Thank you very much. Any question? Yeah.
Images get processed in science. I mean, for research too, to show as much detail as possible. What do you see is the difference between astrophotography and astronomy science? Or is that the same thing?
No, it's not the same, I think, because you pretend to communicate something visually. in astronomy, we are getting data from the objects, and you are doing your measurements. But one thing is doing measurements, and another thing is to give visual meaning to that image. And in fact, most of the time we process the data in astrophotography in a way that then you cannot make any measurement in your data anymore. Mainly because the eye has a different responsiveness compared to the digital camera. So you cannot work in astrophotography with linear images like we acquire in a digital camera. In some way, astrophotography is very similar to the work of a musician, because you are not able to see the object you are photographing. So imagine a musician trying to play a music score that was composed 200 years ago. You cannot ask the author how to play it. You should interpret do your research on that score and interpret that score. The same happens in astrophotography, thinking always in a visual representation. Yeah.
I had a question about PixInsight. How many years has PixInsight been developed, and how many people develop it?
10 years.
10 years. So.
The developer is one guy. Because I have been working on the development, but I'm not programmer. I have been designing some of the tools and so on, doing beta testing, but I'm not programming there.
Any other questions?
All right, let's thank our speaker again.
Thank you.
Free program, isn't it? Is it a free program?
I don't know.
Kind of.
Thank you.